Section: Introduction. In this section, we discuss how large language models and the transformer architecture have transformed machine learning and are poised to impact various fields like industry, science, and art. Despite their significant influence, the exact ways in which these models develop their useful properties remain largely unclear. Our focus is on the ability of these models to learn from new examples provided through prompts after their initial training is complete. Traditionally, machine learning has viewed pattern extraction as a process where model weights are updated as examples are processed. However, in context learning, ICL, we do not see immediate weight updates, which raises questions about how these models adapt based on user prompts. Researchers have speculated that some form of implicit weight updates occurs during inference when a prompt is used. Recent studies have shown that simplified models of transformer blocks can perform a kind of optimization similar to gradient descent. We build on this idea of implicit weight updates but take a different approach. Instead of simplifying the model, we generalize the transformer block into what we call a contextual block. We demonstrate that when these contextual layers are combined with standard neural networks, they can implicitly convert context into weight updates for the first layer of the network. We provide a specific formula for this implicit update, which is a rank 1 matrix, suggesting that contextual layers can fine-tune the weights of the neural network based on the context provided. We also highlight that large language models can learn from examples in prompts, a capability evident since GPT-3, known as in-context learning, ICL. We question whether this learning is genuine or if it merely retrieves pre-trained capabilities without new learning. Some studies suggest that examples in prompts act more like Bayesian conditioning than true learning. However, we note that while this holds for smaller models, larger models can actually learn from randomly altered labels in prompts. Additionally, the emergence of true ICL seems to depend on the diversity of data during pre-training. On the other hand, experiments show that transformers trained on regression tasks can learn new functions during inference, indicating that they can act as meta-optimizers. Other research has proposed that example consumption during inference can be linked to gradient descent steps through implicit weight updates. Recent findings also suggest that chain-of-thought prompting can mimic multi-step gradient descent updates. However, these dynamics have been shown to rely on specific assumptions about linear layers and regression prompts, which some researchers argue are unrealistic. In our work, we explore the concept of ICL as a result of implicit weight updates without the constraints of linear attention layers and allow for more generic prompts. This brings our theory closer to the actual transformer blocks used in practice, although we must understand the implicit dynamics as occurring on the MLP layer rather than the self-attention layer. Section Summary. In this section, we explore the emergent ability of large language models, LLMs, to learn from context during inference, known as in-context learning, ICL, and propose that this process involves implicit weight updates rather than explicit changes to model parameters. We introduce a generalized transformer block, termed a contextual block, which allows for these implicit updates to occur, suggesting that contextual layers can effectively fine-tune the weights of neural networks based on the provided context. Section: Contextual blocks. In this section, we abstract some important features of transformers. We introduce the concept of a contextual layer, which expands on the self-attention layer found in transformer blocks. Here, a contextual block combines a contextual layer with a standard neural network, broadening the idea of a transformer block. We then present our main theorem, which demonstrates that the context for these blocks serves as a low-rank adjustment to the neural network weights. For simplicity, we focus on a neural network without skip connections, as the skip connection case is more complex and detailed in the appendix. We define a contextual layer as a network layer that can accept a single input vector and produce an output. Additionally, it can take a context along with this vector, resulting in a combined output. We will often simplify our notation by writing the input to a contextual layer as just the two components, rather than showing their concatenation. As an example, we can think of the self-attention layer in a transformer block, where the context is an instruction prompt made up of a sequence of tokens, and the input is a query token. Together, these create a contextualized input prompt. The output of the self-attention layer corresponds to the last token in this prompt. We define the difference between the outputs with and without context as the difference between the two outputs. This leads us to generalize the concept of a full transformer block into what we call a contextual block. A contextual block consists of a contextual layer combined with a neural network, where the neural network's first layer has weights and biases. Our theorem indicates that a contextual block transforms a part of the context into an implicit update of the neural network weights. This means that the weights are adjusted based on the information from the context. Essentially, contextual layers adapt the network weights to fit the context by adding a low-rank update to the original weights. When we consider a contextual block formed by a contextual layer and a fully connected layer, the effect of a portion of the context on the output corresponds to a specific weight update in the first layer. We show that this update is rank 1, meaning it can be represented as a column vector multiplied by a row vector. We conclude our proof through direct computation, confirming that the context vector relates to the outputs with and without the context. Our theorem asserts that any contextual layer facilitates an implicit transfer of information from the prompt to the first layer of the neural network, altering its behavior. Some contextual layers may be more effective than others in providing useful weight modifications. When the entire context is used, our theorem provides a way to transfer all context information into the weight matrix. We can also express the weight transfer formula in terms of the union of contexts. In the appendix, we extend our theorem to neural networks with skip connections, which is common in standard transformer blocks. We will also validate our theoretical findings through experiments in a concrete example. Section Summary. In this section, we introduce the concept of contextual blocks, which generalize transformer self-attention layers by allowing a contextual layer to modify neural network weights through implicit low-rank updates based on context. We demonstrate that the output of these blocks can effectively incorporate context information into the neural network, enhancing its performance without altering the original architecture. Section: The Implicit Learning Dynamics of ICL. In this section, we explore the implicit learning dynamics of in-context learning, ICL. When we have a context represented as a sequence of tokens, we can iteratively apply our findings to reveal how each token influences the output of the contextual block. We begin with an initial weight for the first layer of our neural network and observe how these weights change as we add each token to the context. This process leads us to a series of weights that ultimately reflect the full context's impact on the model's weights. We find that this implicit learning resembles online gradient descent, where each token acts like a data point, and the loss changes with each token added. Specifically, we can express the weight updates as stochastic gradient updates, with a learning rate based on the norm of a function evaluated at a point, and the loss at each step reflecting the difference in outputs caused by adding a new token to the existing context. We note that the change in weights measures the effect of adding a new token to the current context. If the new token does not affect the output, the corresponding weight update becomes 0. Our experiments demonstrate that these gradients diminish as the learning process approaches the full context. Interestingly, we can derive a different but related learning dynamic by considering partial updates that do not alter the overall output at each step. This approach leads to a formula for the final weight that reflects the entire context. To validate our theoretical findings, we conduct experiments on a well-defined problem of learning functions from in-context examples. Previous studies have shown that transformers can learn linear functions from scratch using in-context examples. Our goal is to confirm that the prompts we use can effectively translate into weight updates, allowing the model to make predictions that align with those made using modified weights, even without direct access to the prompts. In our setup, we train a simple transformer on input-output pairs structured as sequences of examples. Each example consists of inputs and their corresponding outputs, sampled from specific distributions. We focus on linear functions, where the output is a linear combination of the input. Our in-context learner aims to predict the output for a new input based on the provided examples. Each training prompt is indexed by a task and can be represented as an embedding matrix. We treat this matrix as a contextualized input prompt, combining the examples and the query input. The model's prediction for the query input is derived from the output of a transformer block. We ensure that the dimensions of the outputs from the model with and without weight updates are consistent. Finally, we train the transformer using a loss function that measures the difference between the predicted and actual outputs over a batch of examples. Section Summary. In this section, we explore the implicit learning dynamics of in-context learning, ICL, by demonstrating how the iterative addition of context tokens updates the neural network weights similarly to stochastic gradient descent, where each token influences the model's output. We also outline our experimental setup to verify that a transformer can learn linear functions from in-context examples, achieving predictions comparable to those made with modified weights, thus confirming the effectiveness of our approach. Section: Verifying Theorem 2.2. In this section, we verify Theorem 2.2. We demonstrate that a transformer trained on linear functions can transfer the in-context prompt to a weight update. Specifically, we want to show that the output of the transformer with weights W and input X is the same as the output with updated weights, W plus a change in weights, and the same input. We compare the validation loss from both sides of this equation when making predictions on an evaluation query token. The loss values from both methods align closely, even when we look at a detailed view of the graph. Next, we conduct experiments to see how the weights change as the model processes the in-context prompt. We aim to confirm that the updates to the weights diminish as we reach context convergence. We create a sequence of weight changes, where each change is defined in a specific way. We expect that as the model processes more of the prompt, the changes in weights should become smaller. We verify this by plotting the change in weights when we add one more context token. We measure this change using a specific mathematical norm and observe that the updates decrease and eventually vanish as the model approaches full context, which aligns with our expectations of gradient descent dynamics. We also compare this process with fine-tuning. We pre-train a transformer model using examples structured in a specific way. For fine-tuning, we create a new test example that the model hasn't seen before, but it comes from the same distribution as the pre-training examples. We then generate datasets for fine-tuning by taking the first few elements of this new example while ignoring the last column, which is our test query. We initialize the transformer with pre-trained weights and fine-tune it using a specific learning rate, updating only the weights of the MLP layer. After fine-tuning on all examples, we calculate the loss on the test query, which we refer to as the gradient descent test loss. We also compute the weight transfer using the context from our fine-tuning process and the same test query. We then plot the gradient descent test loss against the weight transfer test loss, averaging over multiple trials. Although the two processes are different, we find that both fine-tuning and implicit weight updates minimize the loss in similar ways.